Perfect. Got it. Thank you so much, and thank you so much for the invitation to talk a little bit about math, which is always fun to do. So today I would like to talk a little bit about polygons, projective polygons in higher dimensions. So mainly I will talk about projective self-dual polygons, but something that I forgot to mention in the abstract that I decided it would be fun to talk about as well is something called Pentagram Map, and how that also looks like in polygons in higher dimensions. So you get a little bonus for today's talk. Please feel free to stop me if you have any questions. I think I'm not very good at keeping track on the chat, but feel free to unmute yourselves.
I can also keep track of the chat if you want.
Okay, perfect. Thank you, Patrick. Yes, so the motivation of the question that about studying self-dual polygons actually comes from a question by Vladimir Arnold. He was asking to find all projective curves that are projectively equivalent to their duals. And back then in 1994, he said that the answer seems to be unknown even in RP2. Now, if you are an algebraic geometer, probably you're raising your eyebrows right now and maybe saying like, okay, wait, what about conics? We know that those are self-dual curves in RP2, so what are you talking about? The thing here is that the notion of self-duality that we have in the classic algebraic geometric sense is a little bit slightly different to the notion that Arnold had in mind. So what I want to do today is maybe not working first of all, I'm not going to work on this question because it's still open. What I'm going to do is I'm going to shift the question a little bit. And then I will also along the way talk a little bit about what is the difference between the notions of self-duality in the case of curves and so on. In the case of in some cases, I'll show a little bit of what is that difference. So the question that I want to work on, instead of working on curves, first of all, take a curve and think of it as closed. And then because I have, even though I am a geometer, I have a combinatorial heart. So I'll take that curve and I'll consider the discrete version of that. So what is that? Is that I'll work on projective polygons, right? So I'm taking sequences of vertices and then straight lines or like segments of straight lines that connect them. And then I want to find out all those that are projectively equivalent to their duals. Now, Arnold was saying that in the case of two-dimensional projective space, we didn't know so much about that. But that question was partially answered by Dmitry Fuchs and Sergei Tabachnikov, this paper from 2009, I believe. They talk about self-dual polygons. They describe them. They provide the dimension of the moduli space of self-dual polygons in RP2 and CP2. And then they do give a few examples of self-dual curves in 2 dimensions. Then the natural question is, okay, how can we take this to the next step? For instance, can I say something more apart from just 2 dimensions? So that's the question that I'll be working on today. Now, before moving on, because I'm not quite sure, I know that we are all experts, but maybe it's been a long time since the last time that people heard about projective space. Should I review very quickly what projective space is, or should I, or everyone feels comfortable with projective? Are we all good?
If no one protests, you can assume everyone knows projective.
I also saw a few thumbs up, so I guess.
Yeah, this is your time to speak up. And if you don't, then I'll just assume that we all are good with projective space. Something that I want to say is that for our talk, I'll be talking about, when I mean projective space, I'm talking about CP, projective space of higher dimensions. 2, 3, I mean, 2 is already known, but 3, 4, and so on. But some of the pictures that you'll see are going to be real, of course, because we don't have enough technology for that. But yeah, okay, cool, perfect. So then let me skip that. What I do want to review very quickly is the notion of duality. So if you have, like, okay, projective space takes a base of a vector space, right? If I have a vector space, then the dual space is just the set of all linear functions on your space. And there is a natural way of correspond subspaces of your vector space and subspaces of the dual space, right? If I have a subspace of the vector space, I can associate it to the annihilator, that is the set of all linear functions that vanish under that set. And then in that case, for instance, in particular, what happens is that if you have a subset of codimension 1, that is a hyperplane, then there's a way of naturally associated to one function in the dual space, in one linear function, that is one element in the dual space that is defined up to scalar. That means, like, for instance, easy example is that we know that, let's say, planes that pass through the origin in R3 and in general in Rn or Cn are by one equation of this form, right? One linear equation that is very well defined up to scalar. So there you are, right? Like, given a hyperplane, I can associate it to one linear function. So in that case, I can associate hyperplanes in projective space to one point in the dual space. So that means that in the case of polygons, if I want to define a dual polygon, what I can do is, well, I start with a polygon, right? So polygon is going to be a sequence of vertices in the projective space. You can see that the sub-indices of the vertices are a little bit off, but that is just for like technical reasons. We are actually not going to pay too much attention to those sub-indices for now, because this is going to be very, broad. But given a sequence of vertices in the projective space, then I can consider that polygon. And then the dual polygon is just going to be by, I take my polygon and I take consecutive vertices, right, as many as I need, so that they can span a hyperplane. And given that hyperplane, I can consider then the element in the dual space. And those vertices are going to be the ones that make the vertices of the dual polygon. For instance, let's say if you are in dimension 3 and here I have a heptagon, then I take consecutive vertices. So let's say these 3. And these 3 are going to span a new vertex that is going to be corresponding to the dual vertex of the dual polygon, right? So for instance, and again, no need to worry a little about the sub-indices, because those are technical details that we worry when we actually have to do things. But for instance, in this case, this subspace would be what I call B3. It's kind of taking the subindex that is in the middle. And then B3 star would be the vertex of the dual polygon. Okay. So maybe I should stop and ask if there are any questions. I haven't said anything new so far. Just making sure that we are all on the same page. Okay, cool. Thank you. Yeah, I usually like to wait 7 seconds before I move on. I've heard that that is how long it takes us introverts to decide that we want to actually ask the question. So, but yeah, the beginning is kind of odd. It's like, why is she pausing so much? But it's because of that. Okay, so finally, I can tell you then what a self-dual polygon is. So if you have a polygon, right, then I'm going to say that that polygon is M self-dual. If there's a projective transformation that sends the vertices of my polygon to the vertices of its dual, but with a shift, right? So the M here, this parameter here corresponds to the shift that I am seeing when I send the polygon to its dual. And this shift is the main difference between the notion that we have, the classic notion in algebraic geometry of self-duality. In self-duality, you don't have that shift, But when Arnold was asking the question about self-dual curves, he actually was thinking about some shift in the curve, and that's the difference that we see here. So I do want to play with this parameter of shift in the vertices. Now, let me give you examples of that. So for instance, if you have a regular polygon, then regular polygons are self-dual for any parameter m. Now, a fair question to ask would be, what do you mean by regular polygon, right? And what I mean by regular polygon is a notion that Coxeter has, which means that, okay, so let me first talk about Euclidean case, right? So in Euclidean geometry of higher dimensions, Coxeter defines regular polygon to be, I have a point, I have an isometry, and let's say that that isometry has finite order. So I'll look at the orbit of that point under this, the iteration of this isometry, and those vertices, which at some point they will come back, form the vertices of a regular polygon. So for instance, here I have two nice examples of regular polygons in 3 dimensions. And then you take the equivalent class of projective polygons for projective geometry. So that's what I mean by regular. All of these are M self-dual for any M, which is not surprising because there's like, it's very symmetric, right? But what happens if I play a little bit more with the parameter M that I have here? So for instance, here I have examples of 12 gons in 3-dimensional projective space. And I'm showing some cartoons of self-dual polygons. So this one over here, this one over here is 12 self-dual 12 gon. This is 6 self-dual, and this is 4 self-dual. Of course, all of these are just cartoons, but if you want to look at the 3-dimensional picture, you can scan with your phone the QR code, and that should send you to I see Joanna did it. Very good. Awesome. That should send you to GeoGebra, which shows you the 3-dimensional picture that you can play around with your phone and maybe move the vertices. All of those are going to be 12 self-dual 12 gons, 6 self-dual 12 gons, and 4 self-dual 12 gons. What I want you to notice, though, is that if you look at this picture just by itself, you can see how the 4 self-dual 12 gon. Hey, yes, perfect. Yeah, that works. Awesome. I'm glad to know that it works for you. So 4 self-dual polygons, as you can see, they look way more symmetric. Awesome. Compared to the 12 self-dual polygon, right? Like even then, that actually looks nicer compared to the 3-dimensional picture. You can see how the crazy. But 4 self-dual 12 gons, for instance, looked a little bit more symmetric. That 4 self-dual more symmetric than 12 self-dual, right? So the thing about this parameter M is that it allows us to describe polygons. I mean, like what I like to think about them is that this parameter M helps you to study polygons with some degree of regularity, right? Maybe I don't, maybe these ones that are completely irregular, maybe I don't care. I mean, not that I don't care about them, I actually will study them, but when I allow to play with this parameter M, then maybe I'm looking at other sorts of polygons that maybe they have a little bit more, right? They have more abstract beauty, if you will. So those are the objects that I want to work with, that I want to classify, I want to describe them, I want to know how many are they, and so on. So what I want to do is study the moduli space of M self-dual n-gons in projective k-dimensional space. So here you have 3 parameters, right? M, which is the parameter on the shift of the vertices that somehow controls how regular your polygon is. Then naturally M, the number of n, the number of vertices, and finally k, the dimension of your space. And we're going to say that 2 polygons are equivalent if there is a projective transformation that sends vertex 1, A1 to vertex A1 prime, and so on, right, respecting the order. The goal would be to give a constructive description of this space. For today, I think I'm just going to show a little about how, I'll show some results that we have in this regard. The nice thing, if time allows, maybe I'll show a little bit of how we get these theorems and so on. But the cool thing is that the results that we have, even though I will talk about, oh, the dimension of this space is blah. The cool thing about finding the dimension is that actually it works with a constructive, like you actually get a constructive way of counting them. That's basically what is happening here. Of course, there are some technical conditions on M, K, and N, but I'm not going to go over them again. I have them here, but we don't have to worry too much about them right now because, again, this is just going to be very all smooth talk, right? I'm not going to get into the details, all of the details. Okay. And maybe this is time where I can drink a little bit and maybe ask questions. Are we good? Okay, cool.
Is it related to moduli space of stable rational curves or in algebraic geometry, or?
Could you repeat that again, please?
Is it related to the moduli space of rational curves? In algebraic geometry, or?
I've heard that there's some relationship, but with the space of polygons in general. I'm not so sure what is the exact relationship, but it could be. I'm not sure though. But I think that the relationship is in the sense of.
Okay, no problem, no problem.
I think so, but I'm not sure. Yeah, like I've heard a comment of one person about it, but it was just like on an email. Yeah, maybe, but yeah, I'm not sure. Yeah, another question. I think it would be, and I think that's kind of the things that I don't know, that I would like to get more into. Because what we do for studying these polygons, this space, what you do is, if you have an M self-dual n-gon, that is, there's a function, right, that sends vertices in your polygon to vertices in the dual. What you can do is use that function to get yourself a bilinear form, right? So given this function f, I get myself a bilinear form of this form. This is going to be defined up to a scalar. But the nice thing about this bilinear form is that it actually encloses some of the information from your polygon. So for instance, something that we know is that when the parameter of the shift coincides with the number of the vertices, that happens if and only if this bilinear form is symmetric. So that's kind of the things that we do for studying this. We start with this setup, and then you get that, okay, we know a little bit about this bilinear form does keep some of the information of this self-dual polygon in such a way. And maybe let me first say this, that I read a paper, and don't quote me on this, okay? But I've heard that Vladimir Arnold, which he's Russian, right? But then he studied in France for a few years, and he used to say, don't quote me on this, that there was two ways of doing math: the Russian way and the French way. And the French way, according to Vladimir, was that you do theorems that are very general, and then Russians are more like, okay, give me the easiest example, like the easiest result that I can say. Like if I cannot say anything easy, then I don't know anything. That's what Vladimir used to say. I don't know if that's true or not. But let me boil it down, like go back to a very, very simple result that we know in this case. So for instance, in two-dimensional projective space, a result by Tabachnikov and Fuchs is that all pentagons are 5 self-dual. And what I mean by that, right? So here I have a pentagon, and then what does it mean that the number of vertices coincides with the number of the shift? So that means that, for instance, in this case, I have A1, And then B1 plus 5, B6, it would be actually these, the span by these two vertices. So the fact that any pentagon is 5 self-dual tells you that any vertex AI goes to the dual of the space spanned by the vertices that are on the opposite side. So this is a result in 2 dimensions. Now, this result actually generalizes to higher dimensions. What it means is that in general, if I have a k plus 3, so for instance, this is the case where k is equal to 2. If you have in general any k plus 3 gon in projective k-dimensional space, this is always k plus 3 self-dual. So this is a result that I proved last year. And actually, in general, what we can say about, like polygons that are M self-dual with M vertices. So when the shift and the number of vertices coincide, actually the dimension of this space is very nice. It's just this formula. Now, something that I like to do for reference is to have in mind that the dimensions of all n-gons in k-dimensional space is this. So it's kind of half of it, something like that, right? Like here I have a -1 instead of a -2 and then over 2. So just to have a reference, right? Like not all polygons are n self-dual. This is how many we have. Okay. Now, what happens when I change the parameter? Maybe, okay, this is when M was equal to N, which means that the bilinear form that I have here is symmetric. But what happens in the case where M is not equal to N? What we can do is then do the following trick. So if I have a subspace in CK plus 1, I can define its perpendicular. That's going to be, again, right, this bilinear form is defined up to scalar, but it is defined equal, like it's equal to 0, right? Like it, in particular, this is well defined, right? Like I can define the perpendicular space. And then if I have the perpendicular space, I can consider a projective transformation, which is if I have a point, I can take the perpendicular space, and then I can consider the perpendicular space again. In the case when F is not symmetric, this G, this projective transformation is not the identity, is something else. Actually, in matrix representation is this. And one can show that this projective transformation, right, it's actually acts as a cyclic permutation on the vertices, which means that I can use, if I can completely determine what these kind of functions are, right? What kind of matrix representation I have here, that's such that G to the R, where R is equal to N over the maximum common factor between M and N, such that that is the identity, right? Then I can give a construction of the polygon P. So that is the general idea, right? So the idea is that I started with a polygon that is self-dual. Then given that polygon, I get myself a bilinear form. Maybe for some reason I forgot or I lost my my polygon. And what I'm saying is that using that bilinear form, I can reconstruct the polygon that I had, or like M self-dual n-gons using that that function F, sorry, that bilinear form F, and in particular, if I have that bilinear form F, I can get this projective transformation and use this projective transformation, which acts as cyclic permutation of the vertices, to reconstruct my polygon P. That sounds very good. Just to show how sometimes it can get sticky, let me show you how does it look like when I consider the dimension of some cases of self-dual polygons. So the theorem that I had before with M self-dual n-gons, right? It was like very simple. It was just like, boom, this is the dimension. Now, what happens when the parameter on the shift, M, is equal to the number of vertices, N, this is N, right? What happens when the number of vertices is equal to 2 times the shift? Then the dimension of that moduli space of self-dual polygons, it's complicated. It depends on if the dimension of the space is less than the parameter or greater than the parameter. And even then, the dimension of that space depends on the class of mod 4 of the dimension of K, which is way more complicated than what at least my advisor was expecting, I think. But again, let me just like boil it down to something easier. Whenever it gets complicated, I'd like to look at what happens with easier things. So for instance, earlier today, I was showing you these examples of self-dual polygons, right? Self-dual 12-gons. So with the theorems that we have, we are able to, for instance, give the dimension of 12 self-dual 12-gons when the parameter of the shift is 4. That means that was corresponding to this polygon. When M is equal to 6, that would correspond to this other shape. And when M is equal to 8 and 12, right? So as you can see, something that is kind of nice that makes sense is that as I keep increasing M, right, the dimension of the moduli space keeps increasing, which is something that we should expect, right? Like it was kind of, yeah, from the picture, we kind of see that when I decrease this parameter, then my polygon look more symmetric. So I'm expecting to have less of them, right? So there's 2 things that one should notice here from this table. One of them is that I don't have the dimension of the moduli space when M is equal to 2 and when M is equal to 10. So those 2 values are missing here. And the reason for that is because I don't know. It's still work in progress, as I said. There's a lot of things that, of course, I don't know here and that it would be nice to study. But of course, right, in particular, M equals 2 sounds very nice because it's like they're symmetric, regular polygons, right? The other sort of surprise.
But probably you just you have a heuristic guess of how large it will be, right?
I don't have it. I don't like guessing, but maybe like 3. I'll say 3 maybe, but don't quote me on this. But I will expect to be less, of course. Yeah. The other, I mean, like the reason why I also maybe don't enjoy guessing too much is because, for instance, this one was a surprise, right? So when M, as I said, right, it's like, okay, I would expect that when M decreases, then the dimension of the space also decreases. But here I have M equals 0, which is the minimum. However, the dimension is 14, which is bigger than all the ones that we had before, right? So there's a surprise over there that I was not expecting. However, I have 2 proofs of this, so I could bet my life on this result. Yeah, so those are 2 things that one should notice here. Yeah, so that's kind of what I have about self-dual polygons. Maybe if I have a little bit more of time, I can talk a little bit about it more. what I also want to talk about is Pentagram Map, if it's okay with all of you. Okay, so Pentagram Map is this map that was discovered by Richard Schwartz, where the idea is that I have a polygon like this one, and then I can consider, so this is two-dimensional, okay? So I have here a polygon, and then what I can do is I can consider the diagonals, right? And then given the diagonals, this gives a new polygon here, right? And then something that we can do is study this map. This map is very popular, you know, it has integrably behavior in many different senses, in many different ways. It has connections with cluster algebras, Friese patterns, octahedral tilings, Y patterns. It's good for your health. It's gluten-free. I don't know. It's great. It's great for a lot of good reasons. One can, for instance, there's a lot of things that one can say about it, right? So for instance, one question would be, I have this pentagram map, and then I can keep it iterating, right? So if I have this polygon, and then I have this new polygon, I can iterate again to find a new polygon. Those polygons are getting smaller and smaller and smaller, and I'm interested on what is the limit of those. Maybe I them, so I rescale them, right? I look at the shape of them, and then I want to see what is the dynamics that are happening over there. So Pentagram Map is highly studied, it's very popular. We all, like, everyone loves Pentagram Map. The thing about Pentagram Map is that it can be defined in higher dimensions. There's no one way, not like only one way of defining Pentagram Map in higher dimensions. But one way of doing it is, what I'm gonna do is I'm gonna start with two multi-indices. So this one over here is gonna kind of tell me how to construct hyperdiagonals. So this one, let me write it here. Hyperdiagonals. So this is kind of going to tell me how to construct these diagonals that I had in 2 dimensions. And then this other parameter, J, is going to tell me how can I intersect these hyperdiagonals. So this governs the behavior of intersection. So if I have these multi-indices, then I can define the pentagram map as follows. So first of all, for these hyperdiagonals, for this subindex I, the hyperdiagonal defined as this one. Now let me give you an example, because with subindices you can get lost very easily. So for instance, here I'm taking k, dimension k equals 3. If I have dimension k equals 3, then I need a multi-index that has 2 entrances, 1 and 2. And then the diagonals are going to be constructed as follows. So I start with a vertex, A1, and then the next vertex that I'll consider to create my hyperdiagonal is going to be the following one. That's what this 1 means over here. If I have 1, then I'm jumping to the next one. And then 2 means that I'm skipping 1, 2, and then this is going to be the next vertex to consider. So these 3 vertices that I have highlighted in purple are spanning the diagonal that I call D1. And then the 2, for instance, right? D3, for instance, would be I start in A1, then I jump, maybe this was not the best color. Let me try this one. I started here in D3, right? And then D1 tells me I jump to D5, and then from D5, I jump all the way to D9. And these 3 vertices span the new diagonal D3, and so on. Okay, so that's what this first sub-index is telling you, how to construct these diagonals. And then, given those hyperdiagonals, the map is going to be a new polygon that is taken by taking the intersections of diagonals, but which hyperdiagonal do you intersect? That depends on this intersection, this multi-index that keeps track of intersections. So for instance, let me go back to example, because there's a lot of sub-indices and it's very easy to like get lost in them. So for instance, here I had, this is the same multi-index that I started with in the previous example, right? So I had 1, 2. So that is telling me that I equals 1, 2, giving me the structure of how to construct the hyperdiagonals. And then j equals 1, 1. It's telling me that I take consecutive hyperdiagonals to intersect. So I have D1, D3, so and then D5, and the intersection of all of these three is going to give me the first vertex of the pentagram map, of the image of the polygon under the pentagram map. And then for the next vertex, then I'll consider D3, D5, D7, and that will give me the second vertex and so on. Okay, so as you can imagine, it can get sticky with multi-indices and whatnot. That's why it's not like one unique way of defining pentagram map in higher dimensions. There's a lot of papers about how to define different pentagram maps, but this is the one that I will go for. Something that is known about pentagram map, for instance, one of the very classic results is the fact that if you have a pentagon, then when I look at the image under the pentagram map, that new polygon is projectively equivalent to the original polygon. So that means that the pentagram map is fixed for pentagons. So that's something that is known in 2 dimensions. Now, something that we found using, a conjecture, let's say, that it's found using a computer, is that if I have, again, right, in higher dimensions, the equivalent of pentagons are k plus 3 gons in projective k-dimensional space. So there are multi-indices j and I, which are here, so that the pentagon, the k plus 3 gon and the image of that k plus 3 gon on their pentagram map, they are projectively equivalent. Again, this is a conjecture, it's not proved. However, the experimentation that was done with the computer support this up to dimension 200. So that feels kind of solid. And of course, there are a lot of other questions that maybe one could like start by exploring using like computations, right? And then getting an idea of what would be a good idea for using, to find I and J and then start proving things. As I said, there's a lot of things here that I don't know the answer of. So I don't know what is the dimension of moduli spaces of M self-dual n-gons for arbitrary parameters M, N, and K. That's something that is still a work in progress. Maybe a more ambitious thing would be to actually understand what are these, not only the dimension, but like the topology of it, like how does this space looks like? What is this moduli space looking like? And then of course, like the rainbow, the golden pot at the end of the rainbow would be actually the original question from Vladimir Arnold about, okay, what can we say about self-dual curves? One can also ask what happens with billiard maps, with billiard trajectories, what's up with them? Because in 2-dimensional case, we know that if you have, for instance, Poncelet polygons, those have some nice terms about self-duality, so maybe something in higher dimensions would be desirable. And then, of course, knowing a little bit more about pentagram map and all of that things would be nice. And here's the references, Arnold, of course, the work by Tabachnikov and Fuchs, And then all the things that I talked about today can be found in a paper that I just submitted to archive. Well, okay, just submitted it last year in December. Yes. I don't know if there are questions.
So are there any questions?
Hi, thanks for your talk. Can I ask a random question?
Yes, please.
So, yeah, so going back, so actually I also I haven't seen this before, so I didn't really know what to expect. But going back to this question about the general topology of these spaces, is there anything you can say about, say, for example, connected components for some specific family? Do we expect these to be really messy, or on the order of I don't know. This is a random question, but let's say, for example, for never connected components, how big do we expect that to be in terms of M and K, for example?
Yeah, that's a great question. So for instance, this theorem is kind of not complete, right? I'm not showing the complete picture of this theorem. Actually, the result is that in this case, you actually have several components. You have, I believe, I'm not, I think I will have to check the paper, but if I'm not wrong, in this case, you have K over 2 floor, number of components. I have the dimension for each one, so you can label each one of these components and actually get the dimension for each one of them. And that's why you have this, the dimension that I have here, right? It's actually showing the dimension of the component that has the highest dimension. And that's why you have kind of this weird behavior with mod 4, because at the end, you're maximizing that, but then the maximum, you want that to be an integer number, and that depends on the residue of K mod 4 in this case, turns out. So yes, there's a lot of that. And yes, I would expect that the components that you have of your polygon actually depend on this G. So actually this G turns out to be, it turns out to be very well understood. It's basically, you can write it as, so you can have let's say, part of the identity, direct sum with a part with a symplectic form, and then direct sum with some, let me call it R. It's kind of rotational. It has some components of the form 0, 1, e to the I theta 0. And then the components come from the different ways that you can write so that it acts as a cyclic permutation. Yeah, so that's why the topology of this space would be very interesting to look at, I think. Ambitious, but interesting.
Thank you. Yeah, it's nice that it sort of explains all the shape of some of the theorems earlier.
Yeah, no, thanks for asking.
All right, are there any other questions?
Yeah, so just one small one. So I'm not really familiar with the history of this topic. So is there a reason why you consider pentagram maps and not other n-gon maps? Why, what's the reason behind the pentagram maps, for instance? Is it because it's the smallest of the ones which are interesting in the sense that?
Well, so I mean, there's other topics that one can consider, right? So for instance, I think that I just chose Pentagram Map because it's that's the one that is very popular. But something that you can also consider that I want to also look at is consolid polygons, for instance. Those are known to be in 2 dimensions, to be M self-dual n-gons. But in general, it would be also interesting to look at those. And there are other maps that I'm sure that they would be interesting to look at. Yeah, I chose Pentagram Map because on one hand, I know that it's a very hot topic. A lot of people like it. As I said, they have very lovely behaviors. So why not? Yes.
All right, any other questions? think that was 7 seconds. So I guess there's no more questions. So thank you again for the
Thank
nice
you for
talk.
the great talk. Thanks.
I will stop.